Winnipeg Center Incorporated annual meeting, and just want to start off with a land acknowledgement. The lands from which our members and guests are joining us are located on the original lands of Anishinaabe, Cree, OJ Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories, we acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So again, welcome everyone to our monthly meeting. I would like to introduce our first speaker tonight for the beginner session is Gail Wise. And Gail is going to talk to us all about Leo the Lion. Please welcome Gail Wise.
Today we are going to take a look at the King of Beasts. This is one of only a few constellations that actually looks like what it's supposed to represent. Leo is a fairly compact constellation, so it is very easy to recognize. The lion's head and mane are made up of a group of bright stars that we call the sickle. But of course, anyone can plainly see that it's really a backwards question mark. The right triangle makes up his backside and his tail. Leo used to have a long, beautiful tail, but it was chopped off around 240 BC to invent the constellation Coma Berenices. The Greeks knew this constellation as simply lion, and it's fairly easy to make out the shape of a crouching lion in its stars. Now see how on the old star charts like this one, Leo had a long, beautiful tail that curves around. There's a star there, Beta Leonis, or Denebula, whose name really means the lion's tail, really. On the dome of the sky, the lion's tail used to extend straight out behind Leo, and the constellation the lion took up a much larger area of the sky. The Greek, Egyptian astronomer Ptolemy and others considered a modern-day constellation, which we call Coma Berenices, where there's an actual star cluster in a very visible in a very dark sky. And that star cluster was the tuft at the end of Leo's tail. Coma Berenices was considered a part of Leo until it was listed as a separate constellation. That story tells us about Queen Berenice and how she honored her love for her husband who went off to war. A few days after their wedding, he took off to attack Asia, and Berenice was grief-stricken at the thought of never seeing her husband again. She was so concerned that she made a vow to the gods that if he returned to her safely, she would cut off her beautiful hair and place it in the temple. In time, he did indeed return to her, and, faithful to her word, Berenice cut off her hair and placed it in the temple as an offering to the gods who had watched over her husband. From there, it was placed in the sky in honor of her sacrifice. The only one who should be unhappy about this story is proud Leo the lion, because he lost the tuft of hair that was at the end of his tail. Leo has had his highest point in the sky on April 1st, and he's very easy to find. If you take the two stars at the end of the pole of the hammer, and instead of going up to find Polaris, point down, and you come to Regulus, which is the bright star. Regulus means little king. This is a blue-white star. Its magnitude is 1.4, so it's very bright. It's 84 light years away from us, and it shines 160 times brighter than our sun. It lies almost exactly on the ecliptic, so once a year, on August 23rd, it's eclipsed by the sun. Of course, we can't see that because it happens during the day, and sometimes it's occulted by the moon. Regulus is a multiple star system. It has an 8th magnitude companion, and its companion has a companion which is 13th magnitude. And there's even a 4th companion here, but that one's only optical. It isn't gravitationally a part of the system. It was Copernicus who named Regulus because it was seen as heaven's guardian, one who regulates all things in the heavens. Before that, the star was known as Coriolanus, which means the lion's heart. Leo no longer has his beautiful long tail, so now the end of him is the blue-white star Denebola. This is an optical double with an orange companion. Regulus and Denebola are both on your Explore the Universe certificate. Gamma Leonis is called Algiba, from the Arabic meaning the forehead. Now this is puzzling, since according to Ptolemy, it lies in the middle of the lion's neck. But the Arabs saw here a much larger constellation than the one that was visualized by the Greeks, so who knows where that was at that time. And Zeta Leonis is known as Adhathara. This is a second magnitude star that's on the Explore the Universe list as well. So you will definitely want to take a look at the direction of Leo. That name is from the Arabic for the braid or the curl, which is a reference to its being in the lion's mane. Zeta is a double star. The primary is magnitude 3, and the companion is magnitude 5.9. The primary doesn't have a fancy name, it's just called 35 Leonis. The main star in Zeta is 274 light years away from us, and the secondary is 100 light years away from us. So Zeta is not a binary system. The two just appear to be together because of our line of sight. When Leo the constellation was first named, the stars of the lion were rising and setting with the sun. The sun was in Leo at the summer solstice. At this point, the sun reaches its maximum power to give life to Earth, and since the lion is the king of beasts, the name Leo the lion was given to this group of stars. Now, I really think it's because it looks so much like a lion. So the lion has been associated with the sun and royalty since very ancient times. Many years ago, the sun was in Leo at the beginning of July. The Chinese summer drought comes to an end in July, so the ancient Chinese saw the curved sickle of stars as the rain dragon, which brings rain. In the Pyramid Age of Egypt, a strange mythological creature that was half human and half animal represented the summer sun. Summer was their most important season because of the rising of the Nile, which led to the life-giving floods that led to the promise of bountiful harvests. At this time of year, lions from the outlying deserts came down into the Nile Valley to seek relief from the heat. Therefore, lions were associated with the beginning of summer. In midsummer, the sun passed from the stars of Leo into Virgo, who represented the harvest. These two groups of stars were in control of the sun during the most important time of the year. And so, when the two signs of summer met, they gave birth to a creature with the body of a lion and the head of a woman, the Sphinx. In Greek mythology, Leo was the lion that Hercules had to kill as the first of his labors. This lion was a fierce beast who descended to earth from a meteor. He ravaged the countryside of Nemea, devouring whoever he met. Nemea is a town in the southwest of Corinth. The lion lived in a cave, coming out every now and then to carry off the local inhabitants, who were becoming scarce. This lion was one tough cat. His hide was so thick that it could not be pierced with a spear or an arrow or any other weapon. Hercules had been placed under an evil spell, which caused him to kill his family in an insane rage. As penance, he received orders from King Eurystheus to perform 12 labors to purge his sin. The first labor was to kill this monstrous lion. It was so well known that Hercules had no trouble finding its cave. As he approached, the lion showed itself, and Hercules shot an arrow right to its heart. The arrow bounced off and fell to the ground. He tried to kill it with his sword, but the sword bent in two. Unfazed, Hercules heaved up his mighty club and beat the lion with it, but the club was smashed to pieces. Hercules battled the lion for a full month. Eventually, he was able to grab the animal and strangle it to death. When he returned to King Eurystheus with the lion, the king thought it was still alive, and he fled in terror at the sight of it. He screamed to Hercules to take it away, so Hercules took it away. He left the city.
For a minute, it was a car in the block with the lights on. Jetta TTM 684. That belongs to you. I came in and the lights were on and they weren't going out. So sorry, don't interrupt.
No. Hercules left the city with the dead lion, and he used the lion's own claws to cut off its tough hide, which he wore as a cloak, and the lion's head became his helmet. Pictures of Hercules almost always show him wearing this armor, which makes him look even more scary and mighty than he really was. The lion's gaping mouth, bobbing above his own head, made Hercules more fearsome than ever. To commemorate this battle, the spirit of the lion was placed in the sky, where it is no longer deadly, it has become beautiful. Leo is far enough from the Milky Way to let us look into intergalactic space. Here you can observe any kind of deep sky object you want, as long as it's a galaxy. The distance to the galaxies in Leo is around 30 to 40 million light years. In general, these galaxies are not very big and flashy, but there sure are a lot of them. And it's pointed out in one of the dome and home things. If you imagine the line there, this looks like a mouse. There's his nose and there's his tail. Do you see it? And point at it. Besides being very dark adapted, the best technique for observing galaxies is using averted vision. By looking slightly away from your target and still keeping your attention on it, you will more easily pick out details like mottling and spiral arms. Leo has 5 Messier objects: M65, M66, M95, M96, and M105. M65 and M66 are a great pair of spiral galaxies that are in the same field, along with NGC 3628. This group is sometimes called the Leo triplets, but I like to say the Leo trio because it sounds cuter. M65 was discovered by our friend Charles Messier, by our friend Charles Messier's friend, Pierre Méchain. It's seen nearly edge-on, and it measures 10 arc minutes by 3 arc minutes, and its magnitude is 9.3. It's very close to its neighboring galaxies, and it's under their gravitational influence. But it looks very much like a typical spark galaxy. It has a bright center with a stellar nucleus, brightly wound spiral arms, and a prominent dust lane. Near the lane, we can see some knots, which is where new stars are being formed. M65 is roughly 35 million light years away. M66 is a little bit larger than M65. It measures 9 by 4 arc minutes, and its magnitude is 9. It was also discovered in 1780 by Pierre Méchain. At the same time, he saw M65, obviously. And it's also about 35 million light years away. It has a central bulge, and its spiral arms are deformed, probably because of its close encounters with M65 and NGC 3628. Its arms seem to have been pulled away from the main disk of the galaxy, and if you use averted vision, you might be able to see some mottling. About 1 degree north is the other member of the Leo trio, NGC 3628. This one was discovered by William Herschel in 1784. This is the faintest of the trio. Its magnitude is 9.5, but it's quite a bit bigger. It measures 13 by 3 arc minutes. It appears fainter just because we see it edge on. If you use low power, you can get all 3 galaxies in the field of your eyepiece. This is a real picture. I did not piece these together. Another trio of galaxies in Leo is M95, M96, and M105, although these are a little bit farther apart. M95 is a typical barred spiral with nearly circular arms. It was also discovered by Pierre Méchain in 1781. This galaxy is about 38 million light years away. It's roundish. It's 7.3 arc minutes by 4.4 arc minutes. It has a bright core, and its magnitude is 9.7. M96 is the brightest of this group of galaxies. Like M65 and M66, these Messier objects weren't exactly discovered by Charles Messier, but by the French astronomer Pierre Méchain. He was mostly responsible for finishing Messier's work. M96 is about 38 million light years away. It has a bright center and very faint circular spiral arms. Including its arms, it's about 100,000 light years in diameter. This is oval, 7.8 arc minutes by 5.2 arc minutes, and it has a bright core. The core is non-stellar. It's about 1 arc minute in diameter. This is a tight spiral, and at magnitude 9.3, it's a little bit brighter than M95. This is a very typical spiral galaxy that we see near the face on. These two galaxies are in the same field of view. They're only 42 arc minutes apart. About 1 degree to the north of these two, and in the same low-power field, we have M105. This one is magnitude 9.3, and it's also 38 million light years away. It was also discovered by Pierre Méchain in 1781. Every picture of M105 also includes NGC 3384 and NGC 3389, which is a much distant background galaxy. Another very nice little galaxy in Leo is NGC 2903. This somehow escaped Charles Messier's telescope, but do not let it escape yours. I really like this one. It's bigger than any of the Messier objects. It measures 12 by 5.6 arc minutes, so it's really huge for a galaxy. And its magnitude is 8.9, which makes it brighter than any of the Messier objects. It's just 1.5 degrees south of the lion's nose, which makes it very easy to find, which is one reason I like it so much. Do you get that email from Top Sky and Telescope every Friday? I got it today, and they talked about Leo, and they mentioned that this galaxy looks like a little mouse at the end of Leo's nose waiting to be pounced on. This is a barred spiral with a nice symmetry. It has a 1 arc minute core and 2 faint arms. It gradually gets brighter towards the middle, and the nucleus appears a little bit off-centered towards the east. There are many, many, many more galaxies in Leo than just these few. Most of them are between Regulus and Denebula, with a few scattered around Gamma. Most of them are quite small, so the larger the telescope, the better. I think we all know the Leonard's meteor shower in November 17th, but did you know that Leo has all these other meteor showers? Some of them don't have very much to them, though, like most of them seem to be in February and March, so when you're out doing your Messier marathon, that's what you're probably seeing. At the northwest corner of Virgo, and extending over the border of Coma Berenices, is the faint Virgo cluster of galaxies. This is an old picture, ignore Mars there. Here's a hint for you Messier hunters. You can use the tail star of Leo as a starting point of finding the central group by allowing the Earth's rotation to sweep the telescope across the positions in the sky. Here's how. Let's say you're using a telescope at 48 power that shows a 1 degree field. That's your typical 8-inch Dobsonian with a 25 millimeter eyepiece. Find the lion's tail star and center it in your eyepiece. Now move the telescope slowly east until the first faint fuzzy just appears at the edge of your field. And this is M98. Now just watch as M98 slowly drifts across the field, and it will be replaced by M99 5 minutes later. And then 10 minutes after that, M88, and then M91. And there will also be smaller, dimmer galaxies strolling across the field. To pick up M85, which is an elliptical galaxy, go back to Denebula and move your telescope 3.5 degrees north. This is where your Telrad circles will come in handy. Then move east to the first fuzzy, which is NGC 4032. It's quite small, only 3.6 but by 3.2 arc minutes, but you can find it. Then just let the view drift by the various objects until you come to M85, which will take about 15 minutes. Just enough time to go into the warm room and make a cup of hot chocolate. You can also continue your scan further east to pick up M53. This is a globular cluster, which is really in the constellation Coma Berenices, but it's a very pretty one, and it's fairly easy to find. It measures 14.4 arc minutes in diameter, and its magnitude is 7.7 with a bright nucleus, which is about 2 arc minutes in diameter. And I was trying to find a few other Leos. That's the mascot of the BC Lions. His name is Leo. And the MGM lion, his name is also Leo. And just to the north of the constellation Leo is the little constellation Leo Minor, the little lion. Little is right, because this constellation is very small and very faint. Its brightest star doesn't even have a proper name, and you'll need very, very dark skies to even glimpse it. But that's okay, because the more felines there are up there, the happier I am. I knew there was a reason I like this hobby. The end.
So we're just a couple minutes early. So, right, well, I just want to wait till 7:30 for people that might join at 7:30, so that's all. So what I want to do, though, just to fill in a little bit of time, is to talk about some different books that you may, or at least tonight, just talk about one that you may want to share or look at. And the one I'm going to talk a little bit about tonight, to fill in some time, is Dot to Dot in the Sky series. And this particular one is Stories of the Aurora. Where's the... Does it look like I'm going in there? Can you see that? Yeah, that's good. That's good. So that's the book for those outside. And all it is to try and talk a little bit. We always, like, Gail started out in her talk, and it was a lot about, you know, the Greek mythology and different things like that. But sometimes it's good to look at all the different things that come in different worlds and different places. You'll see things from different perspectives and different stories. So for instance, just for a couple things, I'm not going to read a full story, but I'm going to read a little bit out of the book. And the author is Joan Marie Glatt, and illustrated by Lorna Bennett. So, and this is, of course, The Young of the Aurora, which recently was pretty popular. There was some pretty fantastic displays recently. I'm going to take my mask off because I keep fogging up. Folklore around the world. Legends associated with auroras often describe majestic creatures existing both on Earth and above. Finnish and Estonian myths tell of a sea monster, possibly a whale, who hit the water with its tail to make beautiful waves of light that rose upward. People who lived in ancient Greenland described the Northern Lights as a glacier god whose powers could only be seen at night. Many stories connected auroras to a spirit world. People in northern parts of Canada, Alaska, and Greenland saw the lights as either being alive or as their ancestors' spirits coming out to show hunters where to find game. In Greenland, auroras were also considered signs from dead relatives and friends who wanted to communicate with those still on Earth. Alaskan Inuit saw the lights as spirits of animals they hunted: seals, salmon, deer, and beluga whales. Northern Aboriginal peoples looked upon auroras as spirit messengers. They believed some men and women could even bring the northern lights lower and make them do their bidding. Inuit, at Alaska's northernmost tip, Point Barrow on the Arctic Ocean, tried to avoid being out at night when the northern lights danced in the sky because they feared auroras could hurt them. If they had to go out, they carried weapons to protect themselves. In Canada's northernmost regions, Inuit thought the northern lights were spirits clothed in mystical lights. They called the fastest moving auroras the dance of death. According to folklore in Norway, you can make the lights dance faster by waving a white cloth. In Denmark, the lights were thought to be caused by flapping flocks of geese stuck in ice in the far north. Their fluttering wings were said to create reflections seen in the northern lights. Meanwhile, ancient Chinese linked the lights with childbirth, as did many tundra peoples who believed that if the lights appeared as a baby was being born, the mother's pain would be lessened, and the child would have a cheerful nature. In Latvia, close to Russia, a red aurora in the winter meant the souls of dead warriors were fighting. The red curtains of light were believed to warn of war, famine, or other disasters. A more cheerful legend from nearby Estonia describes the lights as part of a wedding celebration held in the heavens. Klondike gold prospectors in North America also took a happier view. They said the northern lights were the reflection of a giant gold deposit. Just a few things on how people see things differently. So again, recommend that you look at some different ones and different perspectives. And again, there's lots of other stories, and if we need to fill in here and there before a speaker, we'll probably do that. And you say our speaker's online? Okay, so I'm going to do his introduction, which will bring us pretty close to the 7:30. So again, our speaker tonight, our main speaker tonight is Dr. John Percy, and he'll be speaking about pulsating variable stars, some human interest aspects. And Dr. John Percy is a very active professor emeritus in astronomy and astrophysics at the University of Toronto, where he continues his research on variable stars and astronomy outreach and communication. He was the RASC National President in 1978-80, Honorary President in 2013 to 2017, Editor of the Observer's Handbook in 1971 to 1981, and is a longtime columnist in the Journal of the RAC. Please welcome Dr. John Percy.
Okay, let's see if we can get started here. Do you see my screen?
No. Is it? Yeah. Okay, try that. Try that. Okay, we're good.
Are you good? And can you hear me?
Yes.
Good. Okay, well, I hope we've got the technology all sorted out here. I gave a virtual talk to the Toronto Centre last week, and it unfortunately went nowhere because there was a major technology problem at the Ontario Science Centre where the actual in-person meeting was being held. So I'm hoping that everything goes a little bit better tonight. And what I want to talk to you about is my favorite topic, which is variable stars. Obviously, that means stars that vary in brightness, so they can vary in other respects as well. And they can vary for a lot of different reasons: pulsation, eruption, eclipses, rotation of a spotted star, and so forth. I'm going to talk to you mainly about pulsating variable stars because that's the kind that I work on most often. And the example that I put on the screen here, you'll recognize this if you read your April journal, because my John Percy's Universe column for the journal is about Barcaroni Borealis and other strange stars of that kind. But the point is that what we see here is a star whose brightness changes from roughly 6 down to 14 or 15, which is a factor of something like 10,000. And that can happen in a period of days or weeks, and then the star slowly returns to normal. And I'll tell you why this happens, or at least as much as we know, in a few minutes. Just a potted history here, because this field has been affected somewhat by the biases of culture. The blue column, the blue entry here points out that 2,500 years ago, the very famous philosopher Aristotle maintained that stars were perfect. They were made of a perfect substance called the quintessence, and they could not possibly vary. Not very surprisingly, it was 2,000 years before Western astronomers actually observed and were convinced that stars did vary. But we can trace the history back as far as 3,200 years ago, when there's strong evidence that the Egyptians not only knew about the variability of Algol, an eclipsing star, but they actually knew what its period of variation was. And certainly starting about 2,500 years ago, astronomers in what's now China, Korea, Japan were carefully observing the sky, looking for omens, and they certainly regarded comets, novae, and supernovae as omens. And astronomy of variable stars continued in places other than the West. Very famous observatory in Samarkand, operated by Winnipeg. And then finally, 400 years ago, Western astronomers started to realize stars could vary. A number of very important examples: Tycho Brahe's supernova about 400 years ago. Kepler observed a supernova very shortly after that. And then it was a long time before the next naked-eye supernova appeared. Mira, a very famous variable star, also discovered about 400 years ago, a part of the Copernican revolution, which demonstrated that Aristotle's ideas simply were not correct. And over the last 400 years, there's been a slow accumulation of new discoveries. I've been part of this for about 50 years, and certainly in my view, the pace of discovery continues. So, in very simple terms, this is a pulsating variable star. Its luminosity, and therefore its apparent brightness, rises and falls with some particular period, and that's because the star is expanding and contracting, expanding and contracting. Also changes somewhat in temperature as well, so the star's color varies during this pulsation cycle. So the most important quantity for the pulsating star is simply the period of the pulsation, the time required for one pulsation. I'm going to mention a very important pulsating star, Polaris, and it has a pulsation period of almost 4 days exactly. Now, most pulsating stars pulsate radially. That means in and out. So the star is expanding and contracting in a rhythmic way. But just for completeness, there are some stars that pulsate in more complicated ways. We call that non-radial pulsation. And on these diagrams here, the two different colors are to represent parts of the star that are moving outward and moving inward. An even simpler kind of pulsation is where the poles of the star are moving inward when the equator is moving outward, and vice versa. So that's a simple kind of non-radial pulsation. But I'm not going to say anything more about non-radial pulsating stars, but just here for completeness. Now, many of you are familiar with the famous Hertzsprung-Russell diagram. It plots absolute magnitude or luminosity upwards. The absolute magnitude, of course, becomes more negative as the star is brighter. And then along the horizontal axis is some measure of the temperature, either the spectral class going from OVA, FK, M, and now we have L and T as well. And as the colors suggest here, blue stars are on the left, red stars are on the right. The radius of the star increases as we go from the lower left to the upper right. The stars in the upper right are absolutely huge red supergiant stars. The reason I show this is because the pulsating stars tend to lie on what we call instability strips. There's a whole bunch of pulsating stars that lie on this particular slant here, particularly the Cepheid variable stars, which are the most famous. Then there's a group of pulsating stars to the right here, the red pulsating stars, and a little group of stars over here called the Beta Cepheids, which I worked on back when I was doing my PhD thesis, but I more or less abandoned them some years after that. So pulsating stars exist in certain particular regimes of luminosity and temperature. And so that relates to the actual cause of the pulsation. Now, this is a little bit complicated, but for those stars that are in the Cepheid instability strip, they have a temperature of something of the order of 7,000 or 8,000 degrees on the surface. And what that means is that a little way below the surface of the star, there's a zone which is shown in light brown here, which is called an ionization zone, in particular for helium. So helium goes from the neutral to once ionized and then to twice ionized. And the reason that's important is that when this star is contracting, then it gets hotter, and the helium is ionized. That requires energy. The energy comes out of the energy that's flowing out of the star. So what happens is that this zone here stores some energy, which it can then use when the star expands. So this energy pushes the star outwards, causing it to expand. And then the whole thing goes into reverse again. Now normally, if you had a star that was expanding and contracting, then friction would bring it to a halt. And so a good analogy here is if you're pushing somebody on a swing. If you just give them one push, then eventually their swing will come to a halt. But if you keep pushing them at the right spot in their swing, that is when they're at the bottom, give them a push in the right direction, you can keep them swinging. In fact, you can get them swinging higher and higher and higher, but normally some kind of equilibrium sets in. And that's the case with the pulsating stars as well. Just for completeness, the red stars, the ones that are really cool, they depend more on hydrogen ionization, which occurs at a lower temperature. And those Beta Cephei stars that I mentioned actually depend on an ionization zone of iron, nickel, and cobalt deep within the star. So that's why these stars actually pulsate. So one of the most important properties of stars, pulsating stars, something that we can use them for, is something called the period luminosity relation. That is, there's a relationship between the luminosity of the star, shown here in solar luminosities, and the period of pulsation in days. So on this graph here, it goes from about 3 days up to about 100 days here. Now, this was discovered a century ago by Henrietta Leavitt. And she did this by noting that in the Magellanic Clouds, which were at the same distance, all the stars were at the same distance from the Earth, the stars that were apparently brightest were the ones that had the longest period. So she established the apparent brightness versus period relation. And because all the stars are at the same distance, that translates directly into an absolute magnitude or luminosity relation. Now, 100 years later, astronomers finally got around to renaming this period luminosity relation as the Leavitt law. So we now call this the Leavitt law after Henrietta Leavitt. And why is there a period luminosity relation? Well, it's because both the luminosity and the period depend on the radius of the star. The bigger the radius of the star, the bigger its radiating area. And the bigger the radius of the star, the more slowly it pulsates. It's kind of like the difference between a fiddle and a string bass. The things that are small pulsate more quickly, and the things that are large pulsate or vibrate more slowly. The importance of this is that if you can identify a Cepheid variable star anywhere in the universe, and for instance in some distant galaxy like Andromeda or whatever, and you measure that its period is 30 days, this relationship here tells you what the luminosity of that star is. Let's say it's 10,000 times the luminosity of the sun, and if you compare that with its apparent luminosity or its apparent magnitude, you can immediately get the distance to that star by the inverse square law of brightness. So this period luminosity relation is one of the most powerful tools for measuring the distance scale of the universe. And because of the way the universe is expanding, the distance to the star automatically tells you something about its about the time that's elapsed. So to discover the size scale of the universe and the time scale of the universe, these kinds of stars are particularly important. So Henrietta Leavitt was one of a number of famous women who worked at the Harvard College Laboratory. Sadly, they were paid much less than the men were. That may be why Edward Pickering hired women. He could get more of them for the same budget. But in any case, many of them went on to become famous enough so that they're mentioned in textbooks, as Henrietta Leavitt is. It's a very interesting book called The Glass Universe by Davis Sobel. I recommend it very highly, and talks about the work that was done at the Harvard Observatory a century ago, laid some of the groundwork for modern astronomy. Now, I might mention my own evolution in variable star astronomy. I actually started out as a theoretician, modeling stellar structure, evolution, and pulsation. And just for the younger folks, that was done using decks of computer cards. You punched in your program on cards, fed them into a humongous machine, and then the output came on a line printer, which you had to tear off and try and do something about. But I actually evolved fairly quickly into observing variable stars. That was partly because my primary supervisor, Pierre DeMarc, left for the University of Chicago, and I ended up being supervised by Don Fernie. I refer you to my article in the journal about a year ago about Don Fernie, who played a very important role, not just in astronomy, but in the RASC, where he was national president and made many other contributions. So he became my supervisor, my lifelong colleague. And so I used to go down to the Kit Peak National Observatory in Arizona for 2 or 3 weeks in the fall. Which was good. I accumulated observations. The problem was that it wasn't really compatible with my teaching duties, and I finally gave up on it because I discovered, for instance, that there was a remarkable database available online of visual and photoelectric data that were obtained by skilled amateur astronomers, particularly from an organization called the AAVSO, the American Association of Variable Star Observers. And I became a colleague of their director at the time, Janet Matty, a dear friend and colleague of mine. Sadly, she passed away at an unfortunately early age. But she was one of the great collaborators and friends of mine in my variable star work. And so I got to know a lot of skilled amateur astronomers, both the ones who did visual observations, the ones who did photoelectric observations, and so forth. Around 1980, as the computer revolution kicked in, we started to have remote robotic telescopes, and I collaborated for a few years with Greg Henry at Tennessee State University. We had a robotic telescope, and we gathered long-term observations of certain kinds of variable stars. And this is about the only way that you can get long-term observations. If you go down to Kit Peak, you might get 3 days. If you go to Hawaii and the CFHT, you might get 2 days. But for long-term observations, you need some other strategy. And then more recently, I've discovered another wonderful online database called the All-Sky Automated Survey for Supernovae, or colloquially we call it ASSASSIN. I've written a journal column about that. You can look it up in the journal a few years ago. And that's one of the main sources that I and my students are using these days. I refer it to you. It's perfectly publicly available. You can just go online there and look at light curves of 500,000 stars. Just look at stars, how stars vary in so many different ways. Now, the other interesting thing is that my other research collaborators have been my students. And I've not only been supervising undergraduate research students, but for 25 years we had a program at the University of Toronto called the U of T Mentorship Program, whereby we could take on really bright, interested senior high school students to work on research projects like our undergraduates did. And so these students would be able to develop and integrate their science, math, and computing skills by doing real science with real data. And the sort of key to it was that I would always try and find some small original project for the students to do, which they could complete by the end of the year, by the end of the summer, whatever they were doing. And that we would have a research paper, which could then be published in a journal like the Journal of the AAVSO or Journal of the RASC, with them as a co-author. And this was really a motivating factor. So at the end of the year, there was always a research day here, and so here's 3 of my high school students here, and they made this display here. They've got Christmas lights here to represent stars and so forth. And I still keep in touch with some of these students. So what I want to do for the rest of the talk is to just show you 4 case studies, 4 examples of stars that I found interesting and worked on. Mostly I'm going to talk about the 4th one here, long secondary periods and red giant stars, because the first 3 I've actually written in the journal articles, which you can go back and look up by looking up the index. In particular, as I said, the Arcturone borealis stars were the subject of my April column this year. The other 2 I threw in because they're not very interesting, but I'm sure that even in downtown Winnipeg you can see Betelgeuse and perhaps even Polaris. So in order to set the stage for Polaris here, I just want to remind you that I showed you the Hertzsprung-Russell diagram where different kinds of variable stars lie on it. There was this instability strip where the Cepheids are found. But the stars, as they grow old, use up their fuel, they evolve. They change in their properties and therefore their position. So for instance, the sun starts out on what we call the main sequence, here, and one more. There we go. And the sun will gradually brighten and cool and become a red giant and long period variable star. A star which is 4 or 5 times as massive as the sun starts out as a hot main sequence star, like here, and it evolves across the HR diagram, becoming cooler. It goes across once, that's the first crossing, it comes back, that's the second crossing, goes back again, that's the third crossing. Now, when it's going on the first crossing or the third crossing, it's actually getting larger with time. So its pulsation period should be gradually slowing down. When it's going on the second crossing back towards the main sequence, it's shrinking, and so the pulsation period should be getting shorter. And so by observing this, if we can observe it, it's a direct observation of stellar evolution. Well, yes, we can observe it, and this is the period change for the star Polaris. It isn't actually the period that's being changed, being plotted here. It's what we call the O minus C, the difference between the time when the star is at maximum and when it would be at maximum if its period remained constant. It's kind of like thinking of 2 watches. You've got a Rolex on one wrist and you've got a Brand X on the other one. The Brand X is slowly losing time by 1 second per day. So relative to the Rolex, after 1 day, it's lost 1 second. After 2 days, it's lost 2 plus 1 is 3. After 3 days, it's 3 plus 3 is 6. And it accumulates in a parabolic way. So if the period is changing, if it's increasing, the parabola turns upwards like this. If the period were decreasing, the parabola would be upside down. It would go like that. But notice how precisely we can measure this here, and how precisely we can determine the rate of period change for the star Polaris. And so this is something that can be compared directly with evolutionary models, the kind that I calculated back when I was first starting out. And so this is how you can directly observe stellar evolution. And by the way, this is something that amateur astronomers do in terms of measuring the time of maximum brightness of a Cepheid, or correspondingly the time of minimum brightness of an eclipsing variable star. And over the decades, amateur astronomers have done a lot of important work in measuring the period changes and hence observing the evolution of the star. So this is all explainable. What isn't explainable about Polaris is that over the last century, the actual amount of variation, the amplitude of the variation, slowly decreased from about 10%, and by the 1980s it was heading down towards 0. This was discovered by Armando Arellano, who was was a PhD student working with me and Bob Garrison. And in 1986, he announced this discovery here. And of course, everybody wondered, does that mean then that Polaris is going to stop pulsating? Is it going to be an ex-Cepheid? Well, unfortunately it didn't, and it's kind of stuck at this point here. But the thing is that we really don't understand why Polaris behaves in this way. It's almost unique among Cepheids for the amplitude to vary, and in particular to actually decrease significantly and to stop pulsating. Of course, it would be great if we could find Cepheids that behave in interesting ways like this. This star here was obviously not being monitored as carefully as it could have been, because there was an interval of like 20 years here when it was doing things nobody was quite knowing. So that's Polaris. The next star, another one that you all are familiar with, is Betelgeuse, the famous red supergiant in the constellation Orion. And you may remember that back in February 2020, it underwent what was called the Great Dimming. So it faded down to about magnitude 1.7, where it's normally up around 0.5, perhaps even a bit brighter. And so when this happened, the news media picked it up, and in fact some astronomers tried to publicize this by saying, well, maybe this means that Betelgeuse is finally going to explode as a supernova, which we know it will someday, but we have no reason for thinking that it's imminent. So there was a huge amount, relatively huge amount of media pickup of this particular behavior here. But the point is that I and the AAVSO have been thinking of this star long, long ago. There's a century of data for this particular star, going back, literally a century. And that data is in the database of the AAVSO. And if we simply look at the photoelectric measurements, these are the precise ones made with photoelectric photometers or CCD cameras, you can see something about the long-term behavior of Betelgeuse. Yes, it went down shortly after this to its 1.5 or whatever, but you notice the way it goes up and down here and sometimes goes through these dips here. If you go back far enough, you find out that there was a dimming that was just about the same as the Great Dimming of 2020. The point is that this is what you can learn by having 100 years of data. If we put this data here through a time series analysis or simply look at the life curve here, we find that first of all, it has two periods. One is 388 days and the other is about 2,000 days here. The 388 is probably a pulsation period. The 2,000 day period is what we call a long secondary period, which is going to pick what I'm going to pick up at the end here. And the other thing is that both of these periods have slowly varying amplitudes on a time scale of 10 or 20 periods. And this is something about the pulsation of cool stars like Betelgeuse and red giants and so forth. They have variable amplitudes of pulsation. Nobody kind of seems to know why, and nobody seems to care very much, except that it's an unexplained property of the pulsation of these stars. So I'm simply pointing out here that the century of data is great, and any of you out there who want to work with the AAVSO and extend this database forward, you are most happy to do that, and we will be very grateful for what you do. Okay, on to our core board. Again, you can see the details in my column in April. But the point is that what's bizarre about this star's light curve is that suddenly and unpredictably it fades by up to 10 magnitudes and then slowly comes back to normal. But its properties are equally bizarre. Most stars are about 3/4 hydrogen, 1/4 helium, and about 2% everything else. Our Corona Borealis has about 1% hydrogen, 10% carbon, and the rest is all the other stuff. And this turns out to be due to the previous evolution of the star, as I described in my column in the RASC journal. There's two main theories for how this came about, neither of which is entirely satisfactory. But the point is that this is a star which is very rich in carbon. And what happens is that randomly in time and randomly in direction, this star belches out clouds of carbon-rich gas and dust. This cools, and when the carbon cools, it turns into soot. And if that cloud of soot happens to be between you and the star, then the star fades. And as the soot dissipates away, the star slowly returns back to normal. Well, there's one other thing that these stars do, which is what I'm interested in, and that is that they also pulsate. They pulsate like the Cepheids. They are, in fact, yellow supergiant stars, which are in some respects like Cepheids, so they have much, much more bizarre compositions than the Cepheids do. And these are photoelectric observations from the AAVSO as the star was coming out of one of those fadings. And you'll notice that in an irregular way, the star brightens and fades, not always totally periodically. It didn't kind of get its period right here, kind of got back to there. It has a period of about 47 days on average, and that's been known for 20 or 30 years, something in fact that I've worked on quite a bit earlier. So this is AAVSO data here, and my latest research paper, which has just been released in the AAVSO journal, which by the way is completely open access. If you go to the aavso.org website and click on journal, it has a list of all the current papers, including mine, and you can get more details here. So what I've been doing is using the Assassin data here as a great database for looking for pulsating Arcturoni borealis stars. That, by the way, is the URL for the Assassin data there. This is a newly discovered star here. At least the pulsation is newly discovered. It was known to be an Arcturoni borealis star before that. You'll notice it has a fairly regular variation here. It periods about 43 days. And incidentally, it turns out that the periods for Arcturoni borealis stars differ by a factor of 2 than periods for Cepheids that have the same luminosity and temperature, and that presumably reflects the huge difference in the structures of the stars. Cepheids have normal compositions, and the Arcturoni borealis stars have this carbon-rich, hydrogen-poor composition. One of the reasons that I'm interested in this is that there's some evidence that the pulsation is actually what triggers the ejections that occur here. So that the reason the dust cloud is ejected in some particular direction is because pulsation drove it away. And I'm going to show you a picture of a red giant in a minute or two, which kind of relates to that. In fact, I will show it to you right here. So now I'm into the last little section here, which is a project that I've been working on quite intensively for many, many years, particularly using AAVSO data. A number of my students have been part of this. And it's a mystery of why red giants, or at least almost half of them, show something called a long secondary period. But I want to start just by showing you this high-resolution image of a red giant. This is Phi 1 Gruis. This is the European Space Agency image here. And what you're to note here is that the surface of the star is not uniform. It's very easy to think that the surfaces of stars are as beautifully uniform as a billiard ball, but they're not. And particular red giant stars have huge convective cells of hot gas coming up and cool gas going down and so forth. Now, presumably, our Corona Borealis stars look something like this. They're not completely uniform. So you can imagine that a pulsation might drive material away from these hotter regions and so forth in some random kind of way. So there is this sort of randomness of the appearance of a red giant star like this. So red giant stars pulsate, and I've got 3 examples here. This is from a paper by Igor Szynski, which I'm going to mention in just a minute. Now, on the left here, this is a relatively low luminosity red giant. It has a period of about 30 days. It has an amplitude here of only a few hundredths of a magnitude. This is a larger luminosity red giant. It has a period of about 107 days here. The amplitude is measured in tenths of a magnitude. And then there's this one here. This is a high luminosity red giant, particularly what we call a Mira star. It has an amplitude of several magnitudes and a period of over a year, 413 days. So for the pulsation of red giants, there's a period luminosity relation. Period becomes greater with increasing luminosity because the radius is becoming larger. And there's also a relationship of the amplitude. As the luminosity becomes greater, so does the amplitude. Now this is the pulsation. This is something that we understand reasonably well. And incidentally, another property of red giant stars, particularly the most luminous ones, is they lose mass. They have intense stellar winds that are screaming off at something like 1 solar mass per million years. So that means that half a million years, they can have lost half of their mass. That's in fact what kills them in the end. The mass lost creates a planetary nebula around the core, which shrinks and becomes a white dwarf star. So the pulsation is very important in the sense that it drives this mass loss here. And you'll notice that there are regions where the mass is denser here. These come from something called helium shell flashes. They're an instability within the pulsating star, and they occur maybe half a dozen times during the red giant's total lifetime. Okay, that brings us to the long secondary periods. Now, one of those women working at the Harvard College Observatory 100 years ago was Cecilia Payne-Gaposchkin, who's sometimes regarded as the greatest woman astronomer of all time. She was very hardworking, and of course she had lots of research assistants to help her. And in a monumental paper that she published in the Harvard College Observatory Bulletin, she listed something of the order of 50 red giant stars here, which not only had a pulsation period of tens of days here, but they had a second period that was about 5 to 10 times greater. So here's one. I'll choose this one randomly. T Quator here, 70 days and 1006. And this was extended by Nancy Hauk, and there's a very good paper that lists over 100 red giant stars that have long secondary periods. And it's a database that I and my students have used in order to study some of these stars here. The problem is nobody really knew why these long secondary periods occurred. Now, unfortunately, around 1950, the Harvard College Observatory program was shut down. There was a change of administration at Harvard College. This sort of thing was completely disposed of by Donald Menzel and the people that came after him. And so that kind of photographic photometry rather abruptly ceased. And by the way, there is actually a project underway to digitize all of the photographic plates from the Harvard College Observatory. It's a project called DASH, D-A-S-C-H. It's kind of stalled right now, but I think eventually we'll have full access to that photometry. But along came the AAPSO. And so the AAPSO visual observations of these stars, going back a whole century here, were the main tool that we could use during that time here. Now let me explain what this is. This is a light curve here for a star called Y Lynxus, and it's just a bit fainter than the naked eye can see here. It has a pulsation period of 134.7 days, and so what we've done here, we've binned the observations in 135-day bins to sort of get rid of the pulsational variability. And now we see this red curve here, which represents the average going through here. And this is a 1,259-day period here. So this star has a 1,259-day long secondary period. Pulsation period is 137 days. And we've analyzed many of these stars. I have a brilliant research student, Emily Deeper, here. She now has a PhD and is working in Chile. And she was able to take all this AVSO data here and extract some useful information from it. The sort of techniques that we use here, first of all, simply light curve analysis. I always look at the light curve first because it should tell you what the star is doing. Then you can use something a bit more sophisticated called time series analysis, or specifically Fourier analysis, which shows you the amount of signal for various periods and frequencies. Frequency is 1 over period, so 0.01 is 100 days, and this is 200 days, and so forth. And this star here actually has 3 periods. The main period is 89 days, but it has a second pulsation mode, 160 days here. And then there's the long secondary period down here, 966 days. So this is the kind of analysis that I and my students do. It's not difficult to do. You can learn to do it. The program you need is on the AVSO website. It's called VSTAR. It has a very good manual which you can use and some tutorials and test stars and so forth. And so if you're interested in data analysis, I refer you to the AVSO website and to use VSTAR. Okay, and then the AVSO photoelectric program picked this up. One of my favorite stars is EU Delphini. It has a pulsation period of 60 days, a long secondary period 10 times greater. And again, this is a light curve here. The scatter up and down, that's the pulsational variation here. That's the 60-day variation that you see. And the red curve here is the average, which starts to bring out the 600-day period. So the AVSO photoelectric program has also contributed significantly to the understanding of these stars. Well, then the floodgates came open. The floodgates were a number of massive automated surveys which professional astronomers carried out in the 1990s. The original ASAS, all-sky automated survey, one called MATCH, looking for massive compact halo objects that use gravitational lensing to magnify stars and so forth. And so all of this data became available. This particular set of period luminosity relations here is from a paper by Igor Szynski and his colleagues, building on some really good work Peter Wood published 20 years earlier. Peter is in Australia. So what are we looking at here? Well, we are looking at period luminosity relations. This is the logarithm of the period down here. That would be 10 days, 100 days, 1,000 days there. And this is the apparent magnitude, but since these are all stars in the Large Magellanic Cloud, they're all at the same distance. So apparent magnitude and absolute magnitude are directly related. Likewise for the Small Magellanic Cloud here. Well, what does this show? Well, on the left, there's a number of sequences here, sequence C, C prime, B, and A. These represent pulsation sequences. The longest pulsation periods are the fundamental mode, then the first overtone mode, then the second overtone mode, and so forth. But then there's this D sequence here. This is a sequence of longer periods, 5 to 10 times larger than the pulsation periods. Likewise, in the Small Magellanic Cloud here, again, you have a number of sequences due to fundamental first overtone, second overtone pulsation. And then you've got the sequence D here, which is due to the long secondary periods. Something that's rather suspicious is that the green points here are eclipsing variables. This is where the long secondary period is due to an eclipse. And you notice it's also true there. And so one might have supposed in 2000 that, well, the long secondary periods were some kind of eclipse. But there was a kind of red herring, and that is you normally measure a binary motion by the radial velocity using the Doppler effect. And there was a very peculiar phenomenon that came up when you're measuring the Doppler shift of these stars here, which didn't seem at all to be due to eclipsing stars. So for 20 years, there was a lot of debate as to whether they were eclipsing, whether they were some kind of non-radial pulsation or something totally different than that. Well, this was Szynski's solution here. Szynski's solution was that the long secondary periods are due to a companion, a dust-enshrouded companion, orbiting around the star and eclipsing it every one LSP, and that dust-enshrouded companion was originally a planet which accreted material from the wind of the red giant star and grew into either a brown dwarf, which is sort of just below the mass of a star, or a low-mass star, like an M-type star or something like that. So the idea would be that in the midst of this cloud here is the companion star, which again was once a planet, but has accreted matter and become a dust-enshrouded companion. It goes around. And in fact, the strongest evidence that Szynski came up with was that if you observe this in the infrared, you actually get a second eclipse taking place when the dusty companion goes behind the red giant. Now, the dusty companion has a temperature of maybe 1,000 degrees. It emits infrared radiation and not visual. And so the fact that there's a second eclipse here in the infrared shows that you have to have some sort of infrared source that goes behind the red giant, as well as eclipsing the red giant as it passes in front. I might point out that this diagram here is apparently by Matilda Szynska, age 12, who I assume is one of Igor's young relatives here. I haven't tracked down whether it's his daughter or a niece or something like that. So anyway, this seemed to be the solution to the long secondary period problem. But in fact, there's a number of problems with it, which I and my students are trying to tie up these loose ends. One is the sheer numbers of these. That from the surveys that Szynski and Wood and so forth did, it appears that of the order of 1/3 of all red giants are in systems like this. And because it's a geometrical effect, if you see these systems face on, there won't be an eclipse. And so it must be that about half of all red giants are in systems like this. And the question is, why haven't we found these among the bright red giants that you can see in the sky and that are in the observer's handbook and so forth? Which raises the question of, will this happen to the sun in 5 billion years? When the sun becomes a red giant star, will Jupiter or Saturn become the planet that accretes material from the wind, which grows the planet into a brown dwarf or a low-mass star, producing the dust-enshrouded companion? Another problem is that you find these long secondary periods just as often in globular clusters, and globular clusters are very poor in elements heavier than helium. They are anything from 10 to 100 times more metal poor than the sun is. Now, surely you need the heavier elements, first of all, to make the dust that gets accreted onto the planet, and you presumably may need heavier elements to produce the planet in the first place. So my students and I have looked at a couple of globular clustered Omega Centauri and 47 Tau, and we find lots and lots of long secondary period stars there. Another thing is a little bit more subtle here, and in the Assassin variable star catalog, they actually define a new class of variable stars called LSP stars, which are ones where the LSP variation is significantly bigger than the variation due to pulsation. The pulsation may only be a few hundredths of a magnitude. The period is 30 or 40 days. And if you remember, stars with that period and amplitude are the ones with low luminosities. They're the stars that have not yet been luminous enough to lose mass and have stellar winds and so forth, which seems to be a necessity for getting long secondary periods in the first place. Another little problem goes back to here, and it has to do with, well, why is the relationship between the period and the luminosity so tight? Now, it's easy to know why it's tight for pulsation. I discussed that earlier, that it's because both the luminosity and the period depend on the radius of the star. But for Brzezinski's mechanism here, the luminosity depends on the radius of the star, but the long secondary period depends on the radius of the orbit of the companion around it. And it's not immediately obvious why these two should be related. So I therefore conclude that the problem may not be fully solved yet. It gives my students and I something to do, and we will continue to work on this. You can help us by becoming an AAV observer, either photoelectrically, CCD, or visually, or whatever. And just to remind you why this matters, it's a very common phenomenon in red giants, apparently. We can speculate about whether this will be part of the future of the sun. The formation of these systems may tell us more about how planets form in different kinds of environments, including globular clusters, and about how dust forms, and so on and so forth. So maybe then an astrophysical mystery that goes back 100 years has now been solved with the help of skilled amateur astronomers and skilled students. So I'm going to stop at this point. If you're interested in more about variable stars here, I have written a book, 2007, Cambridge University Press here. I think I can still recommend it. And also the AAVSO, their website contains a huge amount of useful information about variable stars and how you can become involved in it. So I'm going to stop at this point and hope that it's possible for you to ask some questions.
Is it possible that these stars could be measured in other areas, such as polarization of the light, light in the ultraviolet, or even shorter wavelengths? Is there some other ways that you
Okay, let me turn the volume up because I'm not quite getting you. So you're saying that should we observe them at other wavelengths?
Yes, or polarization.
Or polarization. Yeah, that's certainly useful. I mean, one of the problems is that to study these stars, these red giants and long secondary periods, you literally need hundreds or thousands of days of data. And it's been a long time since any professional astronomers have done polarization studies over that period of time. Now, it's true that if the AAVSO or some other group wanted to take up a communal project to do long-term polarimetry of stars like this, that would be great. Infrared measurements are useful. Ultraviolet aren't really, because these are very cool stars here. There's very little ultraviolet. But certainly infrared, visual, photoelectric, maybe polarization if you could learn something useful from it.
We got, Darren's got a question.
Yeah, I've got actually a couple, but I'll start with the one here. When you're doing the period measurements of a lot, can you hear me okay? First of all?
I'll repeat the question to him.
Okay.
That would be good. Yeah, I can't.
So basically, in a nutshell, what I wanted to ask is, like, as you're using some of these variable stars as let's call them galactic or transgalactic yardsticks for measuring distance, do they take into account any sort of relativistic effects that would happen? Because as you go further out, obviously the redshift changes, and does that correlate to the spectroscopy data that you see on these variables as well? So that's one.
Well, the answer to that is pretty easy, that the stars, the Cepheids that we can see are in relatively nearby galaxies, and they're not out to the distances where you need to use any sort of relativistic corrections or anything like that. So this is the relatively nearby universe. Now, for more distant objects, the best thing to use is supernovae. And supernovae are good because the peak luminosity is either constant or it correlates with something that you can measure. So all of the distance measurements to the our universe now tend to be done using supernovae, or at least as far as you can see them. Then beyond that, you have to somehow use a whole galaxy as a kind of yardstick. But no, you don't need to use general relativity for pulsating stars.
I did, yes. With regards to these LSPs, is it possible that, is there any data on some of these LSPs as far as them being maybe a close binary? Maybe not so much that the Roche lobes are touching, but almost maybe kind of special cases where instead of it being a sooty planet, maybe it's a companion that's already gone through a white dwarf stage and is just right on the edge and is pulling actually material off, accreting it and creating the cloud there for, you know what I mean? Is there any data on that? Like, do they look at radial velocities as well as the brightness on these things in some cases to be able to determine whether that's the case?
A couple of different responses to that. If the red giant had a white dwarf companion, then there are various signals that you would expect to see as the material from the red giant encountered the very hot white dwarf in the very deep gravitational well. So Myra, the most famous of the pulsating red giants, does have a white dwarf companion, and that produces all sorts of interesting stuff. Now, a red giant star is of the order of 1 to 200 times the radius of the sun. So that means that anything that's orbiting around it is going to be in a relatively large orbit. I mentioned this business of the type of relation between the luminosity and the long secondary period. What this seems to indicate, according to a study that my student Julia Kim and I did, is that the companion would be about twice the radius of the star away from the center of the star. Now, of course, if the companion was much closer than two star radii away, then it would start to interact with the atmosphere of the red giant. If it were too far away, then first of all, the odds of an eclipse taking place would be smaller, and there'd probably be less chance for the planet to accrete material. But remember that if the sun becomes a red giant, and it comes to be, let's say, the size of the Earth, then Jupiter is 5 times further away than that. Saturn is 10 times further away than that. So it's interesting to speculate whether this is going to happen to the sun in 5 billion years.
In the back, oh, we're good. Okay, Scott first.
With the proliferation of inexpensive CMOS cameras, a lot of people have the capability of doing photography
Yes.
It's been very hard to get filters, the appropriate filters. What kind of project would you recommend, and what kind of passband filter would you suggest people start with? Like there's work being done with just DSLR cameras that can be done, but what kind of data is most useful to a researcher?
Well, it's certainly true that if you can use something like the V filter, that gets you more or less on a standard system. One of the problems with visual observations, as you can imagine, is that everybody's eye is slightly different and your eyes change with age. And so you end up with observations which are not at all on any standard system. So it's great if you can somehow achieve the standard Johnson V magnitude. And if you can get the B magnitude, for a red giant star, you might be more interested in getting R or I, the near infrared and the infrared magnitudes. But I certainly encourage people to try using whatever imaging device they have to do a little bit of science with it. The AVSO is a wonderful resource, and there are people in the RASC who are quite experienced at doing this. And just get to a new dimension in astronomy.
Can you comment on how RR Lyra stars work?
RR Lyra stars.
Yeah.
Okay. Yeah. Yes, these are old low-mass stars, which occur particularly in globular star clusters. They're stars that have become red giants, and then they've been transformed into what we call horizontal branch stars. They have masses about half of that of the sun, because they've gone through the first stages of their evolution. But if they find themselves with the luminosity and temperature that puts them in the instability strip, then they will pulsate. But because they're relatively small, their pulsation periods are more like 0.3 or 0.5 or maybe as much as 1 day. So the pulsation periods are much shorter than the Cepheids. What's kind of nice about that for observers is that you can go out at night, and if you've got 8 hours of observing, then you can follow an RR star through most of its cycle, which is kind of exciting. Or you would have enough observations to be able to time the maximum of the RR Lyra star. The AVSO collects and publishes times of maximum of RR Lyra stars regularly. You'll find it in the AVSO journal. So it's one of their programs that you can get involved with. So again, the RR Lyra stars are very old stars with low masses, as compared with Cepheids, which are relatively massive stars, which are relatively young relative to the sun.
Sorry, I guess I meant theoretically, like you explained how the Cepheids work in terms of the ionization of what's needed. So I'm just wondering.
I didn't hear the whole question, but the pulsation mechanism is exactly the same. And there's another class of variable stars called Delta Scuti stars. These are young stars on the main sequence, 2 or 3 times as massive as the sun. They pulsate with periods as short as 1/10 of a day or 2/10 of a day. They're a lot of fun. One of the first really keen observers that I met was Doug Welch, who has gone on to great things as a professional astronomer, but when he was in his teens, he was an active RASC and AVSO observer, and one of the projects that he took on was the Delta Scuti stars, because some of them do their thing in a very short period of time. In one short night, you can get a whole light curve for these things.
Okay, and we have an online question from Eric Graves, a member of the RASC and active AVSO observer. And
Definitely.
yeah, and his question is, are SX Phoenix stars also pulsating stars? I've heard that undergrads at York University observe them routinely, and I just gave one a shot myself this week, AE person of choice.
Yeah, they're closely related to the Delta Scuti stars and the R-Lyre stars. And they have larger amplitude, so they're even better than the Delta Scuti stars.
Great. And thanks, Eric, for the question.
And thanks to Eric and all the other observers for the great work that they do.
Are there any other questions? Oh, one more. Go ahead.
Yeah, I just had, it's one of your very earlier slides where you showed variable, well, the variable stars you're talking about vary in radius, but then you were showing some asymmetrical ones, and I was wondering why they're asymmetrical modes instead of modes that are more symmetrical. Was it plot you had?
Yeah, the asymmetrical and the non-radial pulsations.
Yeah,
Here at the beginning.
I find it odd that they're asymmetrical.
Well, yeah, you may be referring to the fact that the light curve of a Cepheid, like Delta Cephei, for instance, which is the standard star, is not sinusoidal. On the other hand, if you do theoretical modeling, which I did 50 years ago, the computer tells you that that's what you would expect to get. There's a sort of shock wave that comes out through the outer layers of the star, and that's the particular shape that you get. I can't think of a simpler explanation than that. The non-radial pulsations are a little bit more complicated. They take a lot more computing power to actually figure it out. But it may be that a star is unstable to that particular kind of pulsation. Some stars pulsate in both radial and non-radial modes. Those beta Cephei stars that I mentioned, they pulsate in both. The Delta Scuti stars can pulsate in both radial and non-radial modes. The most complicated pulsators are the white dwarfs. If you find a white dwarf in the instability strip, it can have 100 different periods. All sorts of different non-radial pulsation periods are excited.
Okay, we'll have our last question. Eric?
Yes, I was going to ask you, Dr. Percy, you had mentioned R. Corona Borealis. I just wanted to know if you had any comments on T. Corona Borealis, specifically, maybe if you have any ideas as to, obviously, when it might appear.
That's not one of the stars that's on my regular list. What star is it and what kind is it?
Oh, sorry, it's a T. Corona Borealis, the flare star.
Is that a nova? I can't remember.
Well, yeah, it technically is, but I was just wondering if, because
okay.
it still does vary in brightness, and I was just wondering if you had any comments on when you might, obviously your answer already explains it, so we'll just leave it.
I have no particular comments about that. You can maybe look it up in my book. I don't have my book with me, so.
No problem, thank you.
Well, again, well, thank you very much.
How's the weather in Winnipeg?
It's raining.
It's great.
Peacefully hot here.
There you go. Okay, we're going to take a 10-minute break. We'll reconvene.
Thank you very much. Bye now.
Thank you. Bye. So we'll take reconvene quarter two. Take a 10-minute break. You want a calendar? Abdul has some calendars. Yeah, that sounds good. Okay. So a few things go through here tonight on our announcements. We have Astronomy Day coming up on April 29th. Looking still for volunteers. So Russell is the coordinator for that. If you could please respond to them. If you're interested in attending, we have a day event, and then we have an evening event at Assiniboine Park. As mentioned before, there's calendars for sale. If you see a dual up here, Abdul can wave his hand if you're still interested. Discounted at least $12. OCAM March, the third Thursday of the month. Volunteers from the RASC can get in free if you bring a scope for the presentation afterwards to the public. And Science Rendezvous, which is at the University of Manitoba, is on May 13th. Stan, I think Stan's here. Stan, can you wave your hands if you're interested in volunteering? Stan, want to wave your hands so they know who you talk to?
Pardon me?
Can you wave your hand so people know who you are? So if you want to volunteer for the Science Rendezvous, which is a public outreach event, Stan is our coordinator for that event. NBTANT, which is an outreach for an Indigenous program. Damon Nightshade right here is our coordinator for that. You just have his hand up if you're interested in volunteering or finding out more information. A reminder that the Lockhart Planetarium is now open at the U of M. I'll come back to the RASC National Financial situation in a second. The Glenlee flood situation. So till the end of the month, we're still going to have a porta potty out at Glenlee. At that time, we're going to stop because with the flood forecast right now, we're not sure what's going to happen. Same as the final repairs to last year's flood. We postpone those until we see what happens with this flood. Because there is, if they're forecasting it could be as bad as last year, it will flood. So we're being cautious about that. I'm going to put up a slide in a second about bulk supplies for optic cleaning. And Scott down front here, he'll be the one coordinating that. And of course, just a touch there on the RASC store. I also want to, if I haven't lost it, make mention of a member. Let's see, my luck, it's already disappeared. What is it? Here we go. If I can read it. If you haven't seen it already. Oh boy. Okay, now I'm going to pronounce it terribly. Kirtan Kamala Krishnamurthy has been recognized and is going to be representing Canada on a STEM competition down in Dallas, Texas. And he's a member of the RASC. And the program he is, his project, his science project, it's not RASC related, but he does come out all the time, is focused on the detection of harmful microorganisms in drinking water using deep learning. And what it is, he's developed with a team of others, a phone app to actually, with a paper microscope, check to see if the water is safe to actually drink. So if you think about that, how many places in the world where nobody knows if the water is safe or not, even here in Canada, you go in the backcountry, you don't know whether the water is safe or not anymore. It used to be, not today. So it's pretty cool. I thought I'd just mention that because he is a member of the RASC Winnipeg Center Incorporated, and I think we should recognize other science fields when they happen. Maybe just a little round of applause to them. I know it's not easy.
Thank you so much. Usually it comes, but today it didn't come. Thank you so much.
You're most welcome.
For the support.
So I will talk briefly about the RASC national financial situation. So most, if not everyone who is a member of the RASC received an email from Lisa DeVito, who was the fundraising under contract to fundraise on behalf of the RASC National. So for those that may not be aware, we sent out information, a little bit of information on it. The RASC National has had some financial issues this year. There is a significant shortfall in funding, and which has created a lot of issues. The National Board is working closely with both the National Council as well as the President's Group to work towards a resolution to right the ship, to bring the finances back in line where they should be. So the challenge right now is this began in earnest back in November of last year. Anybody who's ever dealt with a situation where they have to first, to be very honest, you have to stop the bleeding of the money that's going out. You have to make some decisions pretty quickly because otherwise you're going to burn through your reserves and you'll be bankrupt and you'll have to close up shop. So that really is what the first priority of the board was, with some recommendations from the President's Group that went back to the membership as best they can, at the very least back to the Centre Councils, and through the National Council representatives as well. And that's where some things started happening, like the Robotic Telescope Program and Sky News. Things that were bleeding dollars that weren't membership services. So, and then the other things that they had to do was then look at your staffing. Labor is always a large portion. Staffing had grown significantly. In a matter of years, just a few years, we went from 3 employees to 15 employees for 5,000 members. That's a lot of employees for 5,000 members who pay on average $100 a year to be a member. So that had to be looked at. What's happening now is the next step, and it takes time to do these things, and it takes a lot of it. The thing we have to understand is the board is just like anybody else here. We're volunteers. So they've got full-time jobs like all of us, and they're having to find time to deal with some pretty significant issues and make some deep decisions. So the next step that's going through is they're working on a budget, because they have to figure out the coming up budget, as well as is there going to be money if this doesn't happen, and make the budget realistic based on the resources that we have. So that's the next step that they're going through. They're still literally going line by line through the current expenditures to see where money can be saved. So there's more to see, more to come. The big thing is, all we can do is we're down to 1 office staff, who was the previous executive director who's come out of retirement to assist, and they're trying to hire an office administrator. So right now there's only 1 person full-time in the office trying to sort through this stuff. So, and we still have the issues that we had with the, they call it Driven, the platform that's online that supports everything. So there's still those issues. So they are working through it. It is challenging. I can personally say, because I'm involved with it a little bit, that a review of what happened to get us there is happening. But that is not the thing that's front and center. Some people are responding saying, well, we should know, we should do this. And I agree, we will know and have it figured out to prevent it from happening again. But very honestly, the number 1 thing that has to be dealt with is get the budget, the money spending, expenditures in line with what the income is. Otherwise, there's some serious, then we have to go into reserves. And once you start working into your reserves, it's only a matter of time, and that's a very short period of time, that you run out of reserves. Reserves are there for rainy days. Ideally, they're generating income for you to use for other things. So does anybody have any questions? I will answer it as best I can. It's not a lot of information, unfortunately, but it is being worked on. There are many of us at National Council making sure that the review will happen. It's begun, but it will take time for us to get to that stage. Darren?
I know it's a little early, so I don't expect a perfect answer. You may not know this, but I'm just wondering if during your involvement with the national group, if they have kind of an approximate estimate as to when they could, and I know they still have a lot of work to do, but are there any kind of outside kind of worst case scenario projections brought up as to when they might get back on track?
Okay, so right now, this year, when the AGM is in June. When the AGM, at the AGM, they present, they think, they're still working through this, because they're not nowhere done doing the budget. This year will be a deficit. They're hoping that next year will be break even. Okay? So that's the forecast right now. Okay? And again, it's still early, but that was as of the end of March, when we had our National Council update, when they updated National Council. That was their best guess at that time. With the caveat, they were still going through to see what could be and couldn't be realized as far as cost cutting. So, okay? So that at this point, but also we're reminding them that if that doesn't happen, you need to have that backup plan if you have to close the doors. What is the backup plan? So that's not the goal. That's not what anybody wants. Everybody is working towards that. So the goal, and it's very frustrating, and I understand that. I get that, you know. But if you can, and you're going to provide feedback, try to provide feedback that gives some suggestions on things to look at to rebuild the RASC at the national level. Okay? Because again, the people that are at the board, it happened. We can throw sticks all we want, but they're trying hard to fix it. Okay? So there is work happening right now to make this better. We're not better, though, by any stretch. Okay? Go ahead.
Also, there are open positions for the board, and nominations are currently open. And I think that election is in June. Is that right?
Yes, that's at the AGM. Yeah, the elections are at the AGM.
That's right. So if you're interested, and if you have, particularly if you have financial acumen,
Yeah. And there are people that are volunteer that are working with the finance committee, who are accountants and deal with this sort of thing, that are working with that committee specifically to put the plan together, present it to the board as they go along. So, any other questions? Do I have any questions online? Okay.
Dennis, I do have a question about something else.
Oh, sure, go ahead and ask that.
On the Okamic, that'd be next Thursday, what time?
I didn't think to look. It's probably going to.
It's at 7.
6:30 or 7?
It will change with how it gets lighter, right? But it probably still is 7.
I do know, I saw Jerry at a function a couple weeks ago. He did mention that this coming one will be the last one for the summer because of the light
Yeah.
conditions.
Yeah.
So I didn't recall what he said as far as when it was.
it's 8 to 9:30
Jerry.
according to the Okanagan website.
I was going to say by now it's usually 8 o'clock right now.
Well, they used to do a presentation, I think, from 7 to 8, and then at 8 they bring up the scopes.
Well, they started at 8 because by the time
Yeah, now
the hour's presentation is done and it's dark enough to.
so I guess they changed it.
Yeah. Sorry, over here.
Sorry, what's on top?
Pardon me?
What is on top?
Entente is an indigenous organization that works with youth to bring them out to give them a camping experience, and we're going to participate with them in at least one camp. Volunteers come out and show them some scopes and things like that. Did you want to add anything to that, David?
Sure. The owners of Entente are, I guess it's a Métis owner, and their goal is to provide camping opportunities for Indigenous families that may not have access to camping equipment or even a credit card to potentially book a campsite. So what they do is they get various organizations to sponsor families. They'll go out, they'll set up the campsite for them, tents, cots, camping, like all the camping equipment they need. And they're planning on running different theme events. One might be like local medicine, picking something else, but they want to do one that's a stargazing night. They actually include a small telescope with the campsite, but they're asking for a volunteer to basically come out and do a presentation for whatever families are out there that night. It might be once this year, it might be a couple times this summer. So
Where is it held?
their website indicated Kichi-Manitou was the primary place they use. She said that she generally just uses southern Manitoba. I sent another email out to them 3 days ago to see if there's any updates, and I haven't heard anything back yet.
Okay. So just a reminder about groups.io is our primary means of communicating, as well as if you want to be long-term with comment groups or communications groups. And just, you would go to groups.io, or you could go to the RASC Winnipeg.groups.io/G/main, and then from there you would click on find a group. So for instance, Darren has a binoculars observing group, and there's several others on there. Armchair astronomy for the cloudy nights. I have a question over here.
Yeah, is the guy who works with the website around I can talk to today?
Russell is not here right now, but Mark, Mark right there, you might be able to talk to Mark a little bit too. Okay? So yeah, so just there you go. How to get onto that site. What's the forecast for tomorrow? Does anybody have a chance to look at the forecast?
Cloudy.
Okay, so don't even worry about numbers tonight. So the one thing I'm going to do here before I let Brian go is I want to put up that slide. We've got the slide for this equipment, and I'll just explain that quickly. So just while we're getting the slide up to talk about it, Darren Henning, 26, was it 26? In March, had a come out, it kind of grew in scope.
Oh, yeah.
But it started out getting, for binoculars and things like that. And one of the things that happened was they were cleaning the optics with multiple different visual astronomy tools, I guess is a nice way to say it. And what came out of it was some discussions about why couldn't we just, as a lot of people didn't have it, but they've seen how it could be used, they'd like to get some of the cleaning product. And it was briefly talked about, and it was suggested it's a no-cost thing to the RASC Winnipeg Center. So council figured, well, we'll support this, set up a way for people who can place an order, and we're just going to get the slide up to tell you a little bit about what's available, what the costs would be. Now, Scott Young has volunteered to coordinate it, and all it is we do a bulk order, and we get a little slightly better price and other stuff, and then we're willing to bring it in for everyone, provided we get enough usage. But certainly there seemed to be a lot of interest in this for the group that participated on that. Was it a Saturday or Sunday?
Saturday.
A Saturday, yeah. So and by all accounts was an excellent event. So everybody can see it. So again, it's just the idea is that this will be available. Where are we going to post this, Scott?
It'll go up on the groups.io email, and I'll also post a link on social media. The thing there is that the prices are estimated. They should go down a little bit because we're saving a little bit on bulk. It'll depend on how many orders we get. But basically, you download this sheet, you fill it out, and you email it to the address that will be listed on it, and then you order it. The deadline is the end of April. We want to try and get as many things done quickly as we can. And yeah, it's a great way to sort of capitalize on save on shipping and get everything together. And thanks very much to Darren and to James Bass to put all this together.
All right, so it was just so you can see there. So for instance, if you wanted those ice wipes, $16.90, and then again, whatever it is. If you're not sure and you're new and you don't know what you need, I'm going to put Darren on the spot. Darren's over here. If you're not sure what, depending on the type of optics you are, maybe talk to Darren and he can guide you to what you might want. Okay? Again, this is where we've got wonderful volunteers in the center. We've got a lot of expertise in different areas, can guide you if you're new or you're not sure, or do I even need to clean that optic at this time? Those kinds of questions. Okay? Great. So we'll get it set up and for Brian. And then tonight, there won't be a what's new, because unfortunately Dr. Booth is quite ill tonight and unable to attend, so there won't be any what's up, or what's new, sorry. And Brian, when we get it up, is going to do what's up.
All right, hope everyone can hear me. We'll talk about what's up for the month of April 2023 and a little bit of for the next month. Okay, let's talk about the planets. I always start off with the planets, but unfortunately most of the planets will not be really visible during the evening. Most of them are going to be either only evening only and maybe in the morning in the twilight, but some are not going to be visible, such as Jupiter. It'll be too close to the sun. Mercury would be best seen probably in the early evening, but it's going to be pretty low in the sky. And of course, Uranus and Neptune, I don't really talk much about it, but it takes a bit of skill to visually, to look at it through a telescope. But Mars is still quite visible in the evening. It's going to be pretty high, but I'm going to show a little bit more about what I'm talking about. For the events of April, again, we do have a few things. Jupiter's in conjunction to the Sun on April 11th. Of course, Neptune will be 2 degrees north of the moon. The new moon's on the 20th, and of course, right after that, and I do have it? No, I don't have it. Sorry. There's a meteor shower on the 20th. I don't have that here, but I am going to talk about it. I apologize for that. But I am going to talk about this annual total solar eclipse that's happening on April the 20th. I believe we have some people out there. I'm not too sure. I think Jay and Judy.
Jay and Judy, they actually joined the meeting briefly right at the very beginning.
Oh, really? Okay, they're there right now. I'm going to talk a little about it. It's unique. It's a very uncommon type of eclipse. And of course, we'll get on it. Okay, so what we have here is, we do have, of course, Mars, Venus, and Mercury in the early evening. If tomorrow was good, if we did have the meeting for tomorrow night, the members' night meeting, this will be seeing tomorrow, but unfortunately it's cloudy. I looked at the forecast a couple times. Again, I'll talk a little bit more about it later. Again, we have Saturn is 3 degrees north of the moon on April the 16th. And we do have a little bit of the crescent moon. So that's going to be quite nice. On April the 22nd, the moon's going to be 1.8 degrees north of the Pleiades system. Of course, early in the evening again, and you can't really see here, you see these blue dots there. So there you go, that's the Pleiades, otherwise known as M45. All right, moving on. Of course, this is April the 23rd. Again, we do have a bit of the crescent moon. And Mars, again, is be a little high in the evening. And then, of course, we've got Venus just below the crescent moon. That will be April the 23rd. Now, I'm going to talk a little bit about the Milky Way. Unfortunately, it's not going to be much to observe. We're not going to get much of the core. As I have it here, it's around 3 o'clock in the morning that we get part of the core. It will get higher, but really the Milky Way will be pretty low in the sky. So according to the model I have, again, we're probably going to see most of the core until August, September, around the star party. All right, the meteor showers that we have coming up on April the 20th. We do have the new moon. So it's on the 23rd, I said, sorry, and the new moon's on the 20th. So we have a good chance of seeing it, hopefully with what it holds. Forecast originally had promising, but it doesn't look like it. Again, the forecast keeps changing, but maybe for, who knows. But it'd be nice to have a meteor shower where there's like a new moon around, not the full moon. Okay, the high-degree solar eclipse I kind of mentioned about earlier. This is both a total eclipse and an angular solar eclipse. What's special about this is because the curvature of the Earth, a lot of places are going to fall short. So either you have the total eclipse or you have the angular eclipse, but that's because of the curvature of the Earth. Now, what's happening here, I have it mentioned down below here. We have a minimum of 6 kilometers wide. If you have to this center, we get about 6 seconds worth. Not a whole lot, right? And of course, the maximum width is going to be 49 and about 1 minute, 16 seconds. Wow. Okay. But it's a hybrid, so it'd be interesting. I do have the source here, the Observatory Handbook of 2023. This is the page 127. There's a lot more detailed information that I have there, the angle of the sun, the coordinates, and how wide is the path kind of thing. So now I'm going to mention a little bit about the solar activity here. Again, they kind of did something a little different here. Can you see it? No, you can't see it. They added something a little bit more. They had a range of where the solar activity is. Again, we're low in the bell curve here. So I kind of want to mention it because I noticed a couple of weeks ago the states were able to observe a little bit about it. So that's pretty high. So anyways, like I said, I'm going to talk a little bit about the main events, but then of course, I don't have it here. The critical meteor shower, there's a full moon. So no chance of actually seeing it, but great meteor shower. Okay, there we go. Sorry, I apologize for that. I don't know how that slide happened there, but anyways, again, we have the full moon, so it's not going to be really observable. All right, now what about the forecast? Okay, I have it here. The temperature is going to fluctuate a little bit, but it looks like we're going to get back in the cold towards the weekend. Again, it's going to go up and down, but on the weekend, it looks like it's going to get pretty cold. Again, maybe some snow. Because again, I looked at a different model for the forecast, and it looks like we're going to get some snow, definitely rain. Okay, this forecast here, the gray represents total cloud coverage, and the blue represents precipitation for it, how much rain. So we are going to get some more rain. We might get a little bit of snow, but in terms of clear skies, again, last night was more promising, or 2 nights ago was a little more promising around the meteor shower for April the 20th. I think Stan has a question.
The metrics show it clear Sunday evening.
Yeah, that's true. Again, if you look at the same model again just now on my phone, yes, on the weekend it looks like it's going to be clear. That is correct, yes. So the model changed for the 3rd time. So again, hope for the best. You know, I'm planning to go out no matter what. But anyways, I think that's all I have for what's up. Oh, you got another question?
I have an interesting event for those who have seen my viewing the young moon. On the 20th, that evening, the opportunity to see a 22-hour-old crescent moon.
22 hours, yes. You're really big on that. Yes, you mentioned it before, yes.
So that's 22 hours at just after about 9 o'clock.
9 o'clock,
And
okay.
at 9 o'clock, it's going to be about 4 degrees above the horizon.
Oh, okay. Pretty low.
These are extremely challenging to see, but it's just something that I talked to people, and a bunch of people are kind of interested in doing it. So if you want to see an extremely young moon, less than a day old, on the 20th, and I've got details on position of time and position of the moon azimuth altitude.
Yeah, something to look forward to. All right, so that's it. That's what's going to have up for April 2023.
We are going to have a What's New presentation. Scott managed to put one together here briefly, and we're just going to get it set up, and we will do that.
I just made it all up.
It's amazing, you know, with the internet we can say anything we want today.
It's so much easier if you don't have to look up.
It's actually, as some of you know, I work at the planetarium, and so doing what's new and what's up and stuff like that happens for me 3 or 4 times a month in various formats, so it's easy to pull stuff together. What's new? First of all, how many of you watched the announcement of the Artemis II crew, the Canadian astronaut who will be going to the moon, hopefully, eventually? Interestingly, just this week, my boss said, oh, I had a job I was supposed to do and I forgot to do it. I was supposed to mail out all these signed astronaut photos of the last astronaut that came to visit. And so here it is, to the RASC Winnipeg Center, believe in yourself, Jeremy Hansen. When he signed this, he was the new guy who was not assigned to a flight. But now, this is pretty cool to have. So we have to figure out how to, I don't know, maybe we pass it around, everybody gets it for a day, a year or something. We'll have to figure out what to do with that. What's that?
Scan it and have digital copies.
Oh yeah, well, that's not a bad idea, yeah. We were lucky enough to host him at the museum a couple of times. My staff called him Jeremy Handsome. He's apparently a tall drink of water. But anyway, it's great to have a Canadian on the crew. It's 18 months away, maybe even longer than that, because these programs tend to get delayed. But we're going to be watching very closely, and I think it'll be pretty exciting to see. This will be the view. Now, there's one disappointment for me about the Artemis II mission. The first uncrewed mission with 3 crash test dummies aboard went out to the moon, orbited the moon, did all sorts of great stuff, got close to the moon, went far out from the moon, came back. It was like a 30-something day mission. Artemis II, with humans aboard, will not orbit the moon. It will go out towards the moon, loop around it once, and come right back, called a free return trajectory. That's so that if the engine fails, they still come back towards the Earth. Very conservative in terms of what could be done. The first time they went out that way with the Apollo spacecraft, they did go into orbit, and there was the concern about what if the engine doesn't light, but it did. So they're being a little bit more cautious. It means the mission is shorter. It's only going to be about a 10-day flight. But still, that'll be 10 days to watch for sure. Just a little while ago, the Europeans launched JUICE, which is, you know, astronomers and particularly space folks are great at acronyms. This is the Jupiter Explorer, and all the other letters in there, they made up a bunch of stuff to make it as a reasonable approximation of an acronym, a backronym as they say. But the JUICE Explorer is on its way to Jupiter.
And the solar panels opened, and it'll get there in 2031. So I'm excited it got off the ground. Now we don't have to think about it for quite a long time. But it's a great mission because it's going to orbit Jupiter. It's going to orbit Ganymede, Callisto, and Europa, the 3 Galilean moons that have subsurface oceans. And for my money, those are the best places to look for life in the solar system. Forget Mars, forget Venus, forget all those other things. I think there's space squid or something swimming around in those oceans underneath that ice. And JUICE will be probably there to be able to confirm that or not. Interestingly, NASA is launching their own Jupiter probe, Europa Clipper. They launch it next year, and it gets there the year before the European spacecraft. I don't know exactly why that is. I'm sure there's good reasons for it, but so there will be a couple of spacecraft out there with complementary missions, which will be pretty cool. And there's JUICE heading in towards Jupiter and the wonderful moons of Jupiter. Now you might think, well, how do you find life in a subsurface ocean? Originally the plan was, well, you land, and then you turn on heaters, and you melt your way through 10 kilometers of ice or so, and then you turn into a submarine, and then you swim around, and you see what you find. Well, you don't actually have to do that, because out on the moons of Jupiter, ice basically takes the place of rock here on the Earth. There's the solid ice, which is like the crust of the Earth, and then there's the liquid ice, which we call water, and liquid rock on the Earth, we call magma or lava, depending on where it is. That kind of stuff comes up to the surface of the Earth in a place called a volcano. The same thing happens on these moons. There are basically ice volcanoes, or geysers really, because we have that kind of thing on the Earth as well. So there's geysers where that liquid ocean from the subsurface area, the place where life might be, actually comes up to the surface. And not just up to the surface, it shoots way out into space. JUICE and the Europa Clipper can basically fly through those plumes of water. So we don't need to have a spacecraft that turns on heaters and mines through 10 kilometers of ice and turns into a submarine. We just need to fly through the right spot. And you can basically see what kind of life there is. Now, I don't think we will detect my space squid that way. I doubt that anything as big as a squid will come shooting up through a geyser. But bacteria, the most likely form of life, definitely a possibility. If we do find space squid or space kraken or something, that'll be very interesting. And I think the spacecraft would probably lose in that particular case. The James Webb Space Telescope took a picture of Uranus. Every grade 6 boy that's come to the planetarium for like the last 3 days has thought that they invented that joke. I've heard it so many times. It's really cool though, because with the infrared wavelengths that JWST uses, you can see the rings much better than you can in visible light. And so here we've got the most detailed view of the rings. This is even more better than the views that the Voyager spacecraft had when it went zipping by back in the 80s. And this one I didn't have a chance to make the little crossfade, but you remember the Hubble Deep Field. Hubble took a picture of empty space, and it took an 11 or 12-day exposure of a place that was empty of stars, except for 1 or 2, and they found all these galaxies. James Webb Space Telescope pointed at the same area and took 2-hour exposure and got a much higher resolution view of that same area. This is the James Webb version of part of the Hubble Deep Field. I don't know what they're going to call it, but it's going to become famous because it's basically all those little red dots that we were talking about that are like the oldest galaxies and that kind of stuff are now shown in amazing detail. So this one image is probably going to keep a whole bunch of grad students busy for most of their career because there's just so much stuff going on. And James Webb is shooting out these kinds of images every day. It's still mind-boggling how much stuff is coming from that telescope. And frankly, I still can't get over the idea that it worked. It was such a complicated process to put together, and the whole thing worked. So that's pretty amazing. And let's see. there was something else I thought. No, I guess there is not. That's what's new for this month, and hopefully there'll be more stuff coming up soon.
Thank you very much, Scott, especially putting that together on short notice. So again, that concludes the meeting for tonight. Thank you all for coming out. For all those that were joining us by the web, thanks for joining us, and I hope you all have a wonderful evening. For those that are interested, over at Boston Pizza, there's a gathering. So for those that are head there, I'm sure you'll have a good time. And the rest of you, safe drive home and have a wonderful evening. Good night.